Hey everybody, Dr. O here, and welcome to this solutions video for Chapter 4. Let's get started. All right, so the first problem in this unit is wanting us to write the empirical formula for the compounds that we're given. So let's take a look at what we got here. So our first compound is a hydrocarbon. This is called pentane, not that you need to know that. And what we're concerned with when we're trying to figure out the empirical formula is we're concerned about what's in the subscript. So we're going to be concerned with these two numbers right here. And what you need to do is you need to find the least common denominator of these values, which means you have to figure out what number can divide both of these numbers evenly. So if we think about 5, there's only two numbers that you can divide into 5, and one of them is 1 and the other one is 5. Now then the question becomes, can we divide 5 into 12? And the answer is no, not if we want a whole number. So then what we're looking at here in the case of pentane is that this is the empirical formula. So the molecular formula is the empirical formula because we cannot reduce the 5 and the 12 to anything smaller. All right, let's take a look at the next one. So here we've got mercury chloride. And again, we're concerned with what's in the subscript here. And in this case, we have two 2's. So both of these can be divided by 2, which reduces each one to 1. So the empirical formula for mercury chloride is going to simply be 1 mercury and 1 chloride. And then our last one, this is actually called acetic acid. We also call it vinegar. We've got 3 numbers here that we need to be concerned with, but the good news is that they're all divisible by 2. So the first number is going to reduce to 1, the second number in the subscript is going to reduce to 2, and the last one is also going to reduce to 1, and our empirical formula ends up being 1 carbon, 2 hydrogens, and 1 oxygen. All right, question 4.2 wants us to use the Lewis dot method to predict a formula for a compound that is formed by the ions of magnesium and nitrogen. All right, so let's go ahead and bring up magnesium. And for this, I do want to bring in the periodic table because that's going to tell us a little bit about the valence electrons in these main group elements. And I'm going to go ahead and label the columns of these main group elements. And the thing that we know about main group elements is that we can predict whether the elements in that column are going to lose electrons to form ions or they're going to gain electrons to form ions. Now, if we look at magnesium, magnesium's right here in column 2. So we know that magnesium is going to have 2 valence electrons. So if we drop those in to our Lewis dot, that's what magnesium looks like. Now magnesium is going to have a tendency to lose those 2 electrons, and it's going to form the magnesium ion with a positive 2 charge. Okay. Now we can move on to nitrogen, and nitrogen is going to be found right here in column 5, which means that it's going to have 5 valence electrons. So here's 1, 2, 3, 4, and our 5th one is right up there. Now, in order for nitrogen to have a full valence orbital, it needs to gain 3 electrons. So it's not going to lose those 5. The odds do not favor losing the 5 electrons that it has, but it does favor gaining an additional 3. So we drop in those 3 right here, and we can reflect that by writing the ion of nitrogen as nitrogen with a negative 3 up in the, or 3 negative up in the superscript. All right, so now our problem is to find the formula for this. And the book doesn't teach you this, but I'm going to teach you this. This is my method, and I call this the red and blue switcheroo. All right, so what we're going to do is we're going to look at the first term, and we're going to take the value, just the value, not the positive or the negative, just the value, which in this case is 2. The value of what's in the superscript for the first term, and then we're going to put that in the subscript of the second term. So then that means our nitrogen is going to have a 2 in the subscript. And then what we're going to do is we're going to take what's in the superscript of our second term, which is the 3, the value of that. We're not worried about the charge, we just want the value, which is 3. And then we're going to drop that in the subscript for the first term, which means then we've got 3 magnesiums. All right. Now we have to prove that we have written a balanced formula here. And what we're aiming to do is to have enough of these ions that we cancel out positive and negative charges, that whatever the charge is being brought to the table by these two cancels out. So let's go ahead and do that. So for magnesium, we know that each magnesium ion brings with it a positive 2 charge. And our formula says that we have 3 of these. And so if we multiply positive 2 plus 3, that's going to give us a charge of positive 6. Now for nitrogen, we know that each nitrogen brings with it a negative 3 charge. And our formula says that we've got 2 of these. And if we multiply negative 3 by 2, that's going to give us negative 6. And we can see that positive 6 brought by the magnesium is going to cancel out the negative 6 brought by the nitrogen. And this confirms that we have written a balanced formula. Now problem 4.3 wants us to do the same thing, except this time we're going to be using potassium and sulfur. All right, so let's bring up our periodic table, and I'm not going to go through the Lewis dot method. We're just going to look at these numbers on top of the columns to predict the ions that get formed. All right, so where is potassium? Potassium is right here. It's a first column element. It's got 1 electron in its valence shell. We know that it's going to lose that 1 electron and form a positive 1 ion. So let's go ahead and write that. So there's our potassium. And then our sulfur is over here. It's in the 6th column, which means that sulfur is going to gain 2 electrons in order to form a stable valence shell, get to that octet. And so we can write sulfur with a 2 negative. All right, so now we still have to find the compound. Got to come up with a formula for the compound, and we're going to use red and blue switcheroo. So we're going to take the positive 1 that's in potassium and put that in the subscript for sulfur. And then we're going to take the, well, we're not going to take the positive 1, but we're just going to take the 1. And then we're going to take the 2 and the 2 negative in the superscript of sulfur, take that 2, and we're going to drop that into the subscript for potassium. And that will make our formula 2 potassiums, 1 sulfur. And it's always a really good idea to start checking our formulas just to make sure that we're writing a balanced formula. So for potassium, we know that each one of these potassium ions is going to bring with it a positive 1 charge. We've got 2 of those in our formula. Positive 1 times 2 is equal to a positive 2. For sulfur, we know that each one of these ions is going to bring a negative 2 to the table. And we've only got 1 in our formula, and negative 2 times 1 is going to be negative 2. And we can see that the positive 2 brought to the table by potassium is going to cancel out the negative 2 brought by sulfur. And we know we've written a balanced formula, and we're done. All right, problem 4.4 is going to have us do the same thing, but we're going to actually encounter something that's going to have us need to pause and consider what it is that we're writing and see if we need to do any augmentation to that formula. So let's go ahead and go through the mechanics here. So we're working with aluminum and nitrogen. Let's bring up our periodic table, and aluminum is here, and we can see aluminum is in the 3rd column, and we know that elements in the 3rd column are going to lose all 3 of those electrons, so we can write aluminum with a +3 in the superscript, letting our reader know that we've lost 3 electrons, leaving behind more positive charge than negative charge. And nitrogen is a 5th column element, which means that it is going to gain 3 electrons. All right. So we can do red and blue switcheroo. So we would take the 3 from aluminum and write it in the subscript for nitrogen, and take the 3 in the superscript of nitrogen and write it in the subscript for aluminum. And if we did that, we'd have a formula that looks like this. But this is kind of a scenario where we need to evaluate what it is that we've got going on here. Now, these are ionic formulas. These are formulas for ionically bounded compounds. And when we write these formulas for these ionically bounded compounds, or these ionic compounds, we don't want to have more elements represented or more ions represented than we really need in the formula. So it's not truly an empirical formula that we're aiming for, but the concept is the same. We want to reduce this number down to its lowest value, because basically what we're saying when we're writing this formula for our ionic compounds is that we're saying we need 3 aluminums to cancel out 3 nitrogens, when in fact we don't really need all 3 of those. So if we think about it, we can divide each one of these numbers in the subscript by 3 and reduce this formula to a 1-for-1. So basically saying that one aluminum cancels out every nitrogen. And we can run the math to prove that. So here's our aluminum, and we know that each aluminum brings to the table a +3 charge. Our formula says we have 1, so the charge that aluminum brings to the table is a +3. We know that for nitrogen, each one is going to bring a -3 to the table, and our formula says we only have 1. We multiply that out, and we're going to have nitrogen bringing a -3 to the table. And we know the +3 of aluminum will cancel out the +3 of the nitrogen, and this way we have written a balanced formula. So when you encounter something like this with these ionically bonded elements, these ionic compounds, you want to reduce what's in the subscript if that's possible. Okay. All right, now what we want to do in question 4.5 is we want to name the compound. So here we're given the formula, and we have to come up with a name. So we've had some naming protocol given in the lecture, and we're going to review those here. So the thing that you need to understand about these ionic formulas is that whatever's in the first position is going to be your positively charged ion, and whatever's in the second position is going to be your negatively charged ion. And the way that you name a positively charged ion is different than how you name a negatively charged ion. So our positively charged ion is called a cation. Negatively charged ion is called the anion. And the way that you set about naming a positively charged ion, in this case we've got this silver here with this +1 charge, is that you're going to, and here's our anion, you're going to take the name of the element. So we're going to name our cation, we're going to take the name of the element, and then we're simply going to name it, follow it with the ion. So silver in its ionic state is simply called silver ion. That's it. That's super simple, okay? Now we have to do a little bit more gyration in order to come up with a name for the anion. Now here we've got the nitrogen, we've got the ion of nitrogen. All right, so let's go ahead and write the name of nitrogen right here. Now what you do to name this anion is you're going to get rid of the ending of the element, and in this case it's going to be this ogen part, and you're going to add IDE, ide, to it. So nitrogen becomes nitride. And that's how you would name all of these negatively charged elements. So chlorine becomes chloride, fluorine becomes fluoride, oxygen becomes oxide, and that's how that follows. All right. So how do we name this compound when we actually put the sodium ion and the nitride together? Well, you're going to get rid of the ion part in the cation, so we're just going to be left with the name of the element, and then you couple it up with the name of the anion. So the name of this compound is going to be silver nitride. Now I am going to go ahead and work the 4 more practice for this one because I think it kind of tests our understanding for a number of concepts. So let's get started with this one. So here they're giving us the name of the compound, rubidium sulfide. And we're going to have to basically figure out what the formula is for this. So it's going to take us through the information that all the other problems have had us work through and see if we can't put it all together in this particular question. All right, so the first thing we want to do is we want to identify the cation and the anion. And we know that whatever's in the first position is going to be our cation. So rubidium is going to be our cation. And how do we name a cation? Well, we take the name of the element and we add the word ion to it. Okay, and then for our anion, we've got sulfide. All right. Now we know that sulfide comes from sulfur, and if we look at it on the periodic table, nope, I guess we're going to go into rubidium. So let's look for rubidium. Rubidium is here. It's a first column element, and that's pretty simple because we know that anything in that first column is going to it's going to form an ion with a +1 charge, and we're given the formula here. So if we write the formula for the rubidium ion is going to be Rb with a plus in the superscript. And for sulfide, we're going to come to sulfur. Sulfur's right here. It's a 6th column element, and we know that elements in the 6th column are going to gain 2 electrons in order to form their ions to get that octet. And so sulfur is going to be written with an S and a 2 negative. All right. So we've identified our ions, and now we have to write the formula. So how are we going to figure out the formula? Well, we're going to do red and blue switcheroo. That's what we're going to do. So we know that we're going to have 2 rubidiums and 1 sulfur. Let's go ahead and write out that formula, and I always like to double check my math. So for rubidium, we know that each rubidium brings with it a positive 1 charge. Our formula says we have 2 of these. Positive 1 times 2 is going to give us a positive 2. And sulfur is going to bring with it, each one's going to bring a 2 negative charge. We've only got 1 in our formula. Negative 2 times 1 is going to be a negative 2. And we can see that the charge brought by rubidium is going to cancel out the charge brought by sulfur, and we have written a balanced formula. So here we took the name. We were able to figure out the ions by looking at the chart, figure out the charges, then back engineer the formula, red and blue switcheroo, and double check our work, and we came up with the name. Actually came up with the formula. We were given the name. There we go. I got it right. All right, problem 4.6 is going to want us to take a look at compounds that are formed with type 2 ions, with metals that form more than one type of ion. All right, so what does that mean? Well, let's just take a look at what we got here. We've got iron and we've got sulfur coming together to form what would be iron sulfide. Now, the trick here is figuring out which version of the metal that we're going to use, which means that iron can form more than one compound. And we've already worked through sulfide. We did that in a previous example. So I'm going to bring up information that we know about sulfur, and it's anion state. So we know that the anion is going to be sulfur. Sulfur brings with it a negative 2 charge. It's called sulfur. It's called sulfide. All right, so we've already figured out all of this in a previous problem. So this is not new information for us. But what is going to be new information is going to be under here, under the cation heading. All right, so how do we know that iron is a type 2 metal, that it's the type of metal that's going to form more than one ion? You'll look it up in the chart. All right. The other thing that you can do is you can look at where it's located in the periodic table, and it is in the group 2 elements. So it's not in it's not in the row in the columns 1 through 8. It's in that dippy any region. That dippy any region of the periodic table, and that's where we're going to find these type 2 elements. And if you're not sure, look it up on a chart. There's no shame in that. So we'll go ahead and do that. So I looked it up in the book just to double check my work, and I want to say it's the chart that's in it's in Unit 4. I want to say it's the chart that's 4.4. And you look it up and you see that iron can form an ion that has a positive 2 charge, and it can form another one that has a positive 3 charge. Now, how are we going to figure out which one to use? Well, we're going to have to kind of think about this. So let's go to the math part when we balanced our, when we did the math to make sure that our formula was balanced, because we are given the formula for this compound, and we do know the charge that sulfur has. What we don't know is the charge that the iron has, but we can figure this out. All right, so we know that our compound has iron in it. We know it has sulfur. We don't really know which iron we need to utilize, but we can figure out something about the sulfur. All right, so we know that our compound here has only one sulfur in it. All right, and we know that each sulfur is going to bring with it a negative 2 charge. So let's go ahead and fill that in, just like we've done in the previous several problems. So we know that each sulfur brings with it a negative 2 charge. Our formula dictates that we have only one. So we know that sulfur is bringing to the table a negative 2 charge. Then that means that whatever iron is, it's going to have to cancel that out. If we come back to our formula, we can see that we also have only one iron, and whatever that is going to have to multiply by a charge that gives us a positive 2 charge. Well, if we come back to our 2 versions of the iron ions, we've got one that has a positive 2 charge and one that has positive 3. If we use the positive 3, we can't multiply that by 1 and get positive 2, but we can with this one. So we're going to end up using this particular iron ion in our formula. So how do we name this? Well, when you have these metals that can form more than one ion, you're going to give it the name of the metal, which is iron, and then you're going to tell it which version of the ion that you're using by putting that in parentheses and with Roman numerals. So we're using iron 2. So we're going to put the 2 in parentheses in Roman numeral 2 in parentheses. All right, and then you're going to put these two names together. So to name this compound right here, we're going to call it iron 2 sulfide. Let's take a look at another one. All right, here they want us to name this compound, and we've got something here that we need to address, and that is what's in the parentheses here. This is a polyatomic ion. Now, you need to be able to recognize that. So the clue is that whatever's in the first position is typically going to be, but not every single time, but typically if it's a metal, it's only going to be one symbol. And in this case, we're looking at the symbol for tin. And then everything after that is going to be a polyatomic ion. Now, do I expect you to know these polyatomic ions by sight and know what their names are and what their charges are? No. I expect you to be able to look it up on a chart. So there's a chart in your book. I believe it's the one that is after the type 2 elements. I want to say it's chart number 4.5. And you're going to look this up and you're going to find a chlorine with 3 oxygens and you're going to give it a name. And you're also going to find out what charge it is, because we're going to have to figure out some stuff about tin. All right. So I'm going to start working with this anion. All right. So I did look this up in the chart, and this is a formula. Okay. So I had to look up to see exactly what what goes here in the superscript, and it is a -1 charge that goes up here. All right. And I looked at the name, and the name is chlorate. And that's all I really need to do. Look it up in the chart, get the charge, get the name, because we have to be able to name the compound, right? Okay, so what is the big deal about getting this charge? Well, I took a look at the type 2 elements chart, and tin is one of those elements that can form more than one ion. All right, so if we bring up the cation category, we basically have tin that can show up with a +2 charge, or we've got another version that can show up with a +4 charge. And we're going to have to figure out which version of tin we're using in this formula in order to name this compound, because we're either going to call it tin 2 or tin 4. Right? Tin 4, good Betty. So we're going to back engineer this, and we're going to start by calculating the charges that our chlorate is bringing to the table. All right, so each chlorate polyatomic ion is going to bring to the table a -1. And if we look up here in our formula, we can see that in this subscript coming after this entire formula for chlorate, we've got a 2. So that we've put this entire chlorate ion in parentheses and then put the 2 on the outside of that, we're telling our reader that we need 2 of this particular ion. We need 2 of everything that's in here, and that we want them arranged so that they create this polyatomic ion. All right, so we're going to have to multiply our -1 times 2, and that means that our chlorate ions bring to the table a total of -2 charge. All right, now if we look at our formula, we know that we've only got 1 tin. All right, so we're going to multiply that tin by 1, and whichever version of tin we have that we're going to use in our formula, it's got to be equal to +2. So which one is it? It's going to be this one right here, and we're going to name it tin, right? So because +2 times 1 is going to be equal to +2. So we're going to name it by its by its elemental name, which is tin, and then we're going to tell our reader which version of the ion that we're using, and that is the 2, and we're going to put that in parentheses and in Roman numerals, so it's tin 2. And then we're going to put these two together, so we're going to have tin 2 chlorate. Right? So I know that a lot of students get hooked up or hitched up on looking at charts. I absolutely encourage chart usage. There's no way that you can memorize who all the type 2 metals are and what sort of charge each one is going to have, because some of them have a +1 ion and a +2. Other ones have a +2 ion and a +3. Some, like tin, have a +2 and a +4. And I don't expect you to memorize that. I expect you to be able to have some idea what you're looking at and find it on a chart. Okay, first of all, recognize, is it a type 2 metal? Is it found there in the second, not the main group elements, but in the second group elements there in the Dippy part of the periodic table? And then take a look at a chart. All right. And as far as things like this chlorate ion, I don't expect you to memorize that. I expect you to have a chart and be able to look this up and figure out if you've got the right formula and then determine what the charge is. Chart usage. It's important. All right, so here we are, question 4.8, and what they want us to do with this one is they want us to name this particular compound. Now you'll notice that I'm not using the language ionic at this point. And how do we know the difference between something that is a molecular compound and something that is an ionic compound? Well, if it's an ionic compound, whatever's in the first position is going to be a metal. And if it is a molecular compound, whatever's in the first position is going to be a nonmetal. It'll be a nonmetal coupled up with another nonmetal, whereas an ionically bonded compound is going to be a metal bonded to a nonmetal. All right, so that's how we know that we're dealing with a molecule. And when we go about naming molecules, the naming protocol is different than how we name our ionic substances. So how do we do that? Well, we actually have to let our reader know how many of our different elements that we have. So for example, with nitrogen, we've got 2 of those. And so we want to let the reader know that when we name this compound. So we're going to include the prefix di, which tells us about the number. And then we're going to next list the name of the element, which is nitrogen. All right, so what's in the first position would be dinitrogen. Now, the next element is going to be oxygen, and we have 5 of those. So we want to tell the reader that we have 5 of them. And so the prefix for this portion of the name is going to include penta, which means 5. All right. And then the name of this second compound is going to be named differently. We're just not going to say oxygen. We're actually going to use the same naming protocol for the nonmetal in ionically bonded compounds here as we did there, which means that we're going to drop the ending of oxygen. We're going to drop that ending, and we're just going to call it, give it the IDE ending and call it oxide. All right, now if we look, we've got this A here and we got an O here. Typically we don't couple up the vowels like this, so we wanted to basically roll off our tongues easily. So instead of pentaoxide, we very likely would just say pentoxide. So putting all of this together, for nitrogen we would call it dinitrogen, and for oxygen we would call it pentoxide. And that's how we would name this particular compound. Now, problem 4.9 wants us to calculate the formula mass of calcium nitrate, which means that, first of all, we have to figure out the formula for it. So we know that we're going to have calcium. All right, so here's calcium in the periodic table, and calcium nitrate. So calcium is a metal, so we know we're dealing with an ionic compound, which means we have to come up with the ions in order to get our formula. So calcium is going to form an ion that has a +2 charge. And then nitrate. Nitrate is not in our periodic table because it's actually a polyatomic ion, which means you have to go to the book and look it up. All right, so you go find a chart somewhere, you can look it up in the book, and you make sure that you're finding the right polyatomic ion, because there's nitrite and there's nitrate. And once you find nitrate, you see that its formula is NO3 and it has a -1 charge. All right, so now that we've identified our ions, we have to come up with a formula. So what are we going to do for this? we're going to do the old red and blue switcheroo. So we're going to take the value of what's in the superscript and switch it and put it in the subscript for the other element or the other ion. So we're going to have 1 calcium and 2 of those nitrates, and so our formula ends up looking like this. Now when you write a formula for a polyatomic ion, it's important that if you have more than one of those, which we do here, you're going to want to put the formula for the polyatomic ion in parentheses and then put however many you need in the subscript after that, because that's telling us that we're doubling everything that's in the parentheses. All right, so we need 2 of these nitrates in order to balance out the charge that comes with calcium. All right, because each one of these nitrates has a -1 charge and calcium has a +2, so that's how we're going to cancel those out. All right, so now with this information, we're going to calculate the formula mass. So we're going to start with calcium, and we're going to go to the periodic table. And down here in the bottom square, we're going to get the atomic mass, not the atomic number. That's up here. That's just telling us the number of protons. We want the atomic mass. Actually, what we're looking for is the average atomic mass, and that's what that value is in the square. Now, I'm going to use the values that are from the textbook. So for calcium, the value that the textbook has is 40.08 atomic mass units. All right, so that's how much each of our calcium is bringing. Each calcium is bringing to the table, and we only have one of those. So we're going to multiply 40.08 times 1. All right, and then to that we're going to add the number of nitrogens, and nitrogen is located over here, right there. And its atomic mass is 14.01. This is actually from the textbook. And we're going to have 2 of those. Now, I know there's only 1 here, but remember, we've got 1 in our formula for nitrate, but we have 2 nitrates, so we have to multiply that by 2. So that's where I'm getting that 2 from. So we're going to multiply 14.01 atomic mass units, which represents the mass of each nitrogen, and we're going to multiply it by 2 because we have 2 of those in our overall formula. And then we have to deal with oxygen. So the atomic mass of each oxygen is going to come in at 16.00 atomic mass units. And how many oxygens are we going to have in this formula? Well, nitrate's going to have 3 per nitrate, but we've got 2 nitrates, so we're going to do 3 times 2 for a total of 6 of these oxygen molecules. All right, so let's go ahead and do the multiplication. So 40.08 times 1 is 40.08. 14.01 times 2 is 28.02. And 16 times 6 is 96. And now we can add all these values together, bringing our formula mass for calcium nitrate to 164.10 atomic mass units. Now you'll notice that I did not round at this point. And the reason why is because I wanted to remain consistent with my significant figures. So all of my values I presented with 2 digits, which means that I want my final value to also reflect with 2 digits to the right of the decimal point as well. So that's why I retained that 0 in my final answer. Now problem 4.10 wants us to find the number of ibuprofen molecules in a tablet that contains 200 milligrams of ibuprofen, and they were kind enough to give us the formula. So if we just read this, there's 3 hints in here that are going to give us some direction on how to solve this problem. So what are the hints? Well, one of them is the number of molecules. All right, they want us to find the number of molecules, which in this case, ibuprofen molecules. They're giving us a mass number right here. So now we have milligrams. And then they're also giving us a formula, right? So these are going to be our 3 pieces of information that are going to basically direct us in how to solve this problem. So when I start by writing these sorts of problems, I like to write down what I'm given. So the thing that I am given is that I'm given 200 milligrams of ibuprofen, and the other thing I'm given is to find the number of ibuprofen molecules. Now, milligrams is a unit of measure, It's a unit, and so are the number of molecules, right? So sometimes students get a little tripped up on this type of problem because they don't recognize that number of molecules can actually be classified as a unit. And this is a dimensional analysis problem. And with dimensional analysis problems, what I like to say is that this is the type of math, the type of problem where you're manipulating the units and the numbers just go along for the ride. Okay, and you're going to see what I mean by that as we set this problem up. All right, so now as we move through this problem, our quest is to take milligrams and then ultimately convert it into number of molecules. And between here, milligrams, and here, molecules, we've got to come up with some conversion factors that are going to get us to where we need to be. Now we're in chapter 4, which means that we're working with things like Avogadro's number. And we know already that 6.022 times 10 to the 23rd number of molecules equals 1 mole. Now this information is important to us because this allows us to establish a conversion factor. So whenever you have information that correlates two different types of units, in this case, number of molecules and moles, then you can use that as a conversion factor. Right? So in this case, what we can do is we know that we've got a relationship between moles and molecules, and we can use this conversion factor to get us from moles into molecules. All right, so far so good. Now we don't know what's just here yet, right? Not yet. But do we know of anything where there is a relationship that establishes a relationship between grams and moles? Well, keep in mind we're here in chapter 4, and one of the things that we've been doing is we've been looking at the periodic table. We've been taking the formula or the formula units of different compounds and figuring out what their mass is. So then, yes, we actually do have some information that will allow us to correlate grams and moles. It starts with the atomic mass unit, but what we know is that atomic mass unit can be converted into molar mass, and the units for molar mass are grams per mole. So then our next conversion factor is going to be grams per mole. All right. So far we're outlining what it is that we need to do to get from milligrams to moles, but we have to tweak a little something that's happening right in this part. So let's talk about that next. Now the first thing that I want to address is what units do we have on top? Well, we have grams on top here in our conversion factor, what's ultimately going to be our conversion factor. And you'll notice that right now I'm just looking at units, right? I just looked at units here. This one's set up and is fine. So what is the problem with the units here? Well, we cannot multiply milligrams by grams and then end up with moles. When you set your conversion factor, you have to make sure that the units that you're looking for are going to be on the top, and that the units that you're trying to eliminate are going to be on the bottom. Now we haven't addressed the milligram to gram issue yet, but we can just look at this as grams. So what we need to do with our molar mass units is we actually need to flip it. And when we do that, we're going to put the moles on top. Okay, and I'll explain why in a little bit more detail. All right, let's talk about how we're going to get out of milligrams and into grams, right? So with this, we're going to have to find a relationship between the number of grams and the number of milligrams. And I'm just going to go ahead and write that in. For every gram, we've got 1,000 milligrams. So that's our conversion factor. All right, now by sketching this out this way, we basically have created the basis for our 3 conversion factors that are going to allow us to go from milligrams to molecules. And the way we're going to do that is we're going to go from milligrams into grams, and then grams into moles, and then moles into number of molecules. Now we've got one more step to go because we have to give this a value. We have to give our moles per grams or grams per mole of value. And the way that we're going to do that is we're going to come back up to this formula and we're going to figure out what the formula mass is and then convert it into molar mass. So let's do that next. So the way we're going to calculate our molar mass is we're going to look at our formula and we're going to find the atomic mass of the element, which in this case our first one is carbon, and the mass is going to be 12.01 atomic mass units. And then we're going to see how many of them we have. So we're going to look here in the subscript and we can see we've got 13 of those. So we're going to multiply 12.01 times 13. All right, now we're going to do the same thing for hydrogen. And if we look at the periodic table, we'll see that the atomic mass of hydrogen comes in at about 1.01 atomic mass units, and we have 18 of them in our formula. And then our next value, which we're going to add, is going to be we're going to look for the atomic mass of oxygen, which is 16.00 atomic mass units, and we have 2 of those, so we're going to multiply it by 2. Now, when we set about doing this calculation, we're going to multiply everything that's got a multiplication involved with it. So we're going to multiply 12.01 times 13, and that's going to give us 156.13 atomic mass units. We're going to do the same thing for 1.01 times 18, and that's going to give us 18.18 atomic mass units. And then we'll finish up by multiplying 16 by 2, which will give us 32.00 atomic mass units. And at this point, we can add all of this up. Now, when we do that, our formula mass is going to be 206.31. And we know that we can convert this into a molar mass by simply just changing atomic mass units into grams per mole. And now we have a value that we can use in our problem to get us into number of ibuprofen molecules. All right, so let's get back to the original sheet and then start plugging in some numbers. Okay, so this is our sketch up on how we're going to solve this problem. So we're going to start by writing what we're being asked, which is to find the number of ibuprofen molecules. And then we're going to plug in our value that has milligrams in it, and that's going to be 200 milligrams. And I'm going to write that over 1. I'm going to go ahead and convert it into a fraction so that all of our conversion factors, you can see what's above the line and below the line, because we're going to start crossing out repeating units. All right. So here's our first value, what's in milligrams, and then the next value that we're going to have to plug in is going to be our conversion factor that gets us out of grams and into milligrams, or gets us out of milligrams and into grams. So that's going to be 1 gram is over 1,000 milligrams. Now, I'm going to pause right here and just talk briefly about setting up a conversion factor. And I said this a moment ago. When you set up your conversion factor, the first thing you have to do is you have to find a relationship between the unit that you're in and the unit you want to move into. So for this conversion factor that's going to get us out of milligrams and grams, we created the relationship that said 1 gram is equal to 1,000 milligrams. And then your question is which one of those values, which one goes on top? And here's my simple rule. And it's true most of the time. There is a caveat. There is a time when this isn't true. But for most of our problems that we're going to be doing, this is going to be the rule, and it's always going to be true. And the rule is that the units that you seek, the units you want to move into, go on top of your conversion factor, which is why I put grams on top and the milligrams on bottom. Now, by doing that, we now see that we've got a repeating unit, which means we've got a unit on top and a unit on bottom. And anything that is on top and on the bottom in these fraction sorts of equations can be crossed out, because you're going to be dividing the top by the bottom. And any value that goes into itself, even a written value, is equal to 1. So we're going to be able to eliminate the milligrams right here. And now the only units that we have are grams. All right. And then the next unit we're going to plug in is our molar mass value with the moles on top. All right, so if we do that, we're going to have 1 mole over 206.31 grams, which is the value that we calculated from our formula for ibuprofen. And we're going to go ahead and get rid of repeating units, which is grams on the top, grams on the bottom. Leaves us only with moles. But we don't want to be in moles. We got one more conversion factor to use. That's going to get us out of moles and into number of molecules. and that's going to be Avogadro's number over 1 mole. And this one is set up because remember the units we seek go on top. This one's ready to go. So I'm going to just drop that one right in. 6.022 times 10 to the 23rd number of molecules. Number of molecules is our unit. It's not like a real unit, but we're going to use it as if it was. And we see we've got moles on the top, moles on the bottom. And at this point, we've eliminated all of the units, and the only units that we have are number of molecules, which is exactly where we want to be. Number of molecules. All right, now we're going to do the math, which means I'm going to multiply 200 by 6.022 times 10 to the 23rd, and then I'm going to divide it by 1,000, and then I'm going to divide it by 206.31. And when I do that, my number of molecules comes up to 5.838 times 10 to the 20th number of molecules of ibuprofen. All right, a couple of things before we close out this particular problem. This value right here, if you go and check it in the book, your last number is a 9 instead of an 8. Now, why is that? Well, it could have been that they used different values for the atomic mass for these elements up here. That's a possibility. And in fact, I'm guessing that that's probably what they did. The other issue could be that they didn't use 6.022. They might have just used 0.62. So that small variation, 1/1000th of a variation, is not a make or break deal in this class. If you gave me the value of 5.838 versus 839, I would still count them both correct. Okay, so there's that. The other thing is why did I include all 4 digits here? Why didn't I just drop this third one and put it in scientific notation? Well, the reason why I kept 4 digits here is because the only number that I'm given in this original equation, this 200.1, it has 4 digits. So it has 4 significant digits, and I want my value to reflect that, my final answer to reflect that as well. So in problem 4.11, they want us to take acetic acid, and they give us the formula, and they want us to calculate the mass percent of oxygen in a molecule of acetic acid. So what are we given? Well, we're given the formula for acetic acid, so that tells us something, and they want us to calculate the mass percent of oxygen in a molecule of acetic acid. Now, we know that there's a relationship between the elements as they appear within a formula, right? And that we can find the percentage of a particular element by figuring out the mass of that element and then the mass of the molecule, and then dividing and multiplying by 100 to get that percentage. So the formula for that is going to look like this, where we're going to find the molar mass of the amount of oxygen in this molecule. We're going to divide it by the molar mass of the molecule. We're going to multiply it by 100%, and that will give us our percentage. All right, so we know what we have to use. What we're going to have to calculate is the molar mass of oxygen and the molar mass of our acetic acid molecule. All right, so for molar mass, we're going to take the molar mass of oxygen, which is 16 grams per mole, and we've got 2 of those. So we're going to multiply it by 2, and that's going to give us a total of 32 grams per mole of our oxygen. That's what our molar mass of oxygen is. The molar mass of acetic acid, well, we're going to take the molar mass of carbon, which is 12.01, and we're going to multiply that by 2 because we have 2 of them. We're going to take the molar mass of hydrogen, which is 1.01. I know I'm kind of rounding up here. And we've got 4 of those, so we're going to multiply this by 4. And then we're going to take our oxygen, which molar mass is 16 grams per mole, and we have 2 of those. And I like to go ahead and do the multiplication. Just to get that out of the way. So 12.01 times 2 is 24.02, 1.01 times 4 is 4.04, and 16 times 2 is 32. Now we can add all this together, and that will give us the molar mass of a molecule of acetic acid. So now we've got the 2 values that we need to plug into this portion of our formula. So let's go ahead and do that. So we're going to take our 32 grams per mole and divide it by 60.06 grams per mole. We're going to multiply that by 100%, and when we do the math, I like to cancel those repeating terms. I love that. And that's going to leave us with 53.28%. Now I know the book is, I'm off a little bit with the book, but if you gave me that answer on an exam, I'd still count it right. Because we can be off in the 100s or even the 1000s and rounding issues. Because I believe the book likes to use 1.008, which can possibly throw that off a little bit. Now, in problem 4.12, they're asking what is the mass of iron. So they want us to know the grams of iron. Oxide contains, let's see, what mass of iron oxide contains 58.7 grams of iron. Okay, so we're given a certain amount of iron, and we want to know how much iron oxide we need to have in order to get that amount of iron. And iron oxide is 69.94% iron by mass, which tells us something too. All right, so in this problem, in the previous problem, and in the next several problems, we're going to be exploring the relationship between molar mass, the percentage of mass of elements within molecules. And so there's going to be a lot of manipulation of that information coming at these concepts from different angles, but basically we're still dealing with the same information. We're typically going to have to come up with molar mass. We typically need a formula. So there's a few things that we're just going to be operating with, and it's a little bit like a shell game where we just kind of keep shuffling things around in order to get what we're asked to get. So that's kind of what we're going to see in these next few problems. All right, so what are we given? Well, we're given that iron 3 is 69.94% of the mass of iron 3 oxide, and there's the formula for that right there. And we're being asked to, we're also being given that we have 58.7 grams of iron, and we want to know how many grams of iron oxide is it going to take to have this 58.7 grams of iron. Okay, now this is one of those sorts of problems where we've got a percentage, and we know that iron is 69.94% of this formula right here, right? So 69.94% iron is going to make up 100% of the iron that we see in the formula. So this is one of those problems where we can take grams. We can just basically interchange the percentage sign with a gram. So we then could say that we've got 69.94 grams of iron in 100 grams of iron oxide. All right, so now that gives us something to work with, right? So the question is how many grams of iron oxide does it take? Well, we can take our grams of iron and we can establish a conversion factor by saying that for every 100 grams of iron oxide, we're going to have 69.94 grams of iron. So we're using this relationship right here to create a conversion factor, because that's what this means, is that for every 100 grams of iron oxide, we're going to have 69.94 grams of iron. We can put that in a conversion factor, and the units that you seek go on top. The units that we're seeking are grams of iron oxide. And we're going to cross out the repeating terms, which means grams of iron go away. The only units that are left are grams of iron oxide. We do the math, which means we're going to multiply 58.7 times 100 and then divide that by 69.94. And then that's going to give us the grams of iron oxide, which is 83.9 grams. So in problem 4.13, they want us to determine the mass of oxygen in a sample of 7.2 grams of aluminum sulfate. So we're looking at basically the same thing that we've been looking at in the previous problems, where we're we need to know the percentage of oxygen in this molecule, and then figure out how much of it is in a 7.2 gram sample. So this is one of those issues, situations where we're going to be using molar mass. We're going to be finding the percent mass. We're going to create a conversion factor, and we're just going to see how we can come at it in a number of different ways. So again, using that information about molar mass, percent mass, that sort of business that we've been doing. So we know that we're given the 7.2 grams of aluminum sulfate. We know that we're given the formula for aluminum sulfate. And we are to find the grams of oxygen in that particular sample. All right, so that doesn't tell us much, but we can establish some parameters, and we're going to be using that business where we say we have 100 grams of aluminum sulfate and then find the percentage of oxygen, and then say we have that many grams of oxygen in here. So that's what we're going to be doing with this. So it means that we have to find the molar mass of aluminum sulfate. And in order to do this problem, we need to be able to understand what is in the subscripts for each of these elements in this problem. And this is going to be critical to working this problem correctly. Right? So for aluminum, we're going to take the molar mass out of the periodic table, which is 26.98 grams per mole. And if we look at the subscript for aluminum, we can see there's a 2 there, and that means we have 2 aluminums in our formula. So we're going to multiply 2 times its molar mass, and that gives us 53.96 grams per mole. The next element is sulfur. So for sulfur, we'll go to the periodic table. We see that its molar mass is 32.07 grams per mole. But how many do we have? Well, sulfur is in parentheses. And whatever's in the subscript at the end of the parentheses, you multiply all the subscripts within the parentheses by that number. Now, there's only one sulfur in the parentheses. So we can assume that there is a subscript of 1 there for sulfur. We're going to multiply that 1 by 3, and that's going to give us the 3 that we see right here. So 3 times 32.07 gives us 96.21 grams per mole for sulfur. We're going to do the same thing for oxygen, and while we're here, let's just look at it. So within the parentheses, we've got 4 oxygen, and we're going to have to multiply that 4 times 3. Right? And that's how I've set it up down here. So the molar mass of oxygen, which is 16 grams per mole, times 4, which is in its subscript, times 3, which is outside its parentheses, and that gives us a total of 192 grams per mole. Now to find the molar mass of aluminum sulfate, we're going to have to add 5396, 9621, and 192, and that gives us 342.17 grams per mole in a molecule of aluminum sulfate. Okay. Now, I am going to go ahead and find the percentage of oxygen in aluminum sulfate. And the way that I'm going to do that is I'm going to take 192 grams per mole of oxygen. I'm going to divide it by the molar mass of the molecule. That's what I'm doing right here. Multiply it by 100%, and that's going to give me 56.11%. Now, I could deviate from how I'm going to solve this, and I'm going to show you another way to solve this at the end of this, but instead, I'm going to do what we've been doing, which is to take this percentage and convert it into grams. So then I can say that I've got 100 grams of aluminum sulfate and 56.11 grams of oxygen. And I can use this information to create a conversion factor that will allow me to get out of grams of aluminum sulfate and into grams of oxygen. So that's what I'm going to do. So I'm going to take my given amount, which is 7.2 grams of aluminum sulfate, going to put that over 1. And with this information down here, I'm going to create a conversion factor. And the units that I seek are oxygen units, grams of oxygen. So I'm going to put that on top in my conversion factor, and then the aluminum sulfate information on the bottom. So it looks like that. Now when I do that, I can cross out grams of aluminum sulfate, top and bottom, leaves me with the units of grams of oxygen. That's all I got. That's good because that's what I'm looking for. And if I do the math, which means I have to multiply 7.2 times 56.11, divide that by 100, I'm going to get 4.04 grams of oxygen. Now if you go to the book and look at the answer gives you 4.0 grams of oxygen. Now why does it do that? Well, it does that because it's looking at the significant figures in the only value that we were given. And we've got two significant figures here, the 7 and the 2. So our answer needs to reflect the same level of significance, which is going to be the 4 and the 0 right here. Now, I said that there's another way to solve this problem, and it has to do with just taking this percentage right here. And so we could take that percentage and multiply that by the value that we're given. So we could take the 7.2 grams and multiply it by 0.5611, which is the same thing as 56.11%. And that would give us 4.04 grams. Now, why do I not like to do that? Well, I don't like to do that because when you set the problem up like this, you're very clear about what it is you're doing. And students, I know how you are because I was once a student myself, and you like to take these shortcuts and you lose track of what it is you're trying to calculate. But with this way, crossing out the repeating units, you know what units you're left in. You know what you need to put in your answer. Here, it gets a little bit ambiguous. That's why I don't like to do it. But if you want to double check yourself, you got a method to do that. In problem 4.14, we are given a sample of a compound that gets decomposed in a lab, and it's going to produce 165 grams of carbon, 27.8 grams of hydrogen, and 220.2 grams of oxygen. And from this information, we should be able to calculate the empirical formula for that compound. And in fact, that is what they do in labs. So let's take what we're given, which is the grams of each one of these different elements, and we should be able to convert this information into an empirical formula. So what do we need to understand about empirical formulas and its relationship to mass? Well, the empirical formula, all the subscripts in the empirical formula basically tell us the moles of an element in that formula. So if we know that the formula is in moles and what we're being given information is in grams, what do you think we're going to be using to get out of grams and into moles? Molar mass. You got it. All right. So we're going to take each one of these values and we're going to convert them into moles by using their molar mass. All right. So that's how we're going to come up with the empirical formula. So we're going to convert the grams into moles. We're going to use the molar mass to do that. So we're going to take 165 grams of carbon and we're going to multiply it by the molar mass of carbon. Now we know that the molar mass is given to us in grams over moles, but we're going to invert that because we want to get rid of the grams and move into the moles. And remember, the units you see go on top. So I'm going to write it kind of funny, but it's the same information. So we're going to have 1 mole of carbon over 12.01 grams of carbon. That means I just basically took grams per mole and flipped it upside down. Now when I do that, I can get rid of my grams of carbon, which is what we want to get rid of, and leaves us with moles of carbon, which is what we want to move to. We do the math and we end up with 13.74 moles of carbon. We're going to do the same thing for hydrogen. So we take our value of hydrogen we got in the decomposition, multiply it by its molar mass, inverted, and the value we get is 27.58 moles of hydrogen. Same thing for oxygen. Its molar mass is 16 grams per mole, inverted. Get rid of our repeating terms and then do the math. We end up with 13.76. All right, so now that we've found the moles of each one of these, we want to establish a relationship between these three values right here. And the way that we do that is we're going to take the lowest number of these three numbers right here, and we're going to divide all three of these numbers by that number. So what does that look like? Well, our lowest number is going to be 13.74, which is the moles of carbon. So for carbon, we'll take 13.74 and divide it by 13.74, and that's going to give us 1. We're going to take the moles of hydrogen, which is 27.58, and divide that by 13.74, and we're going to get 2.007. And we're going to do the same thing for carbon, which is 13.76 divided by 13.74, and we're going to get a little bit more than 1. All right. Now, in doing this, we've established a relationship between all three of these moles, which is basically what we've got in an empirical formula. We've got a relationship between them. We're basically finding the ratios. So these three values right here are going to be the subscripts for our empirical formula. Now we can't put decimal places in, but these values are so low. This is actually, in the 1,000th spot, that we can drop these and just round these down to whole numbers. So that means then that we're going to have one carbon in our formula. Hydrogen, we're going to have two of those. So there's our two hydrogens. And we're going to have one oxygen. And that's how we come up with our empirical formula. So this was pretty simple, pretty straightforward, because we ended up with some, real tiny numbers out here. But if you end up having like a 0.5 or a 0.33 or something like that, we're going to have to do something different. We're going to have to actually multiply it by everything. And we are going to have a problem where we do that. So sit tight. We'll explore this topic a little further in an upcoming problem. So in problem 4.15, we are given some information about the mass percent composition of ibuprofen and asked to come up with its empirical formula. All right. So what we're given is the percentage of carbon, hydrogen, and oxygen that make up the molecule of ibuprofen, and we're being asked to come up with this empirical formula. Now we know that whenever we're given these percentages, we can get rid of the percentages and talk about them in terms of grams, and then if we take a gram of our molecule, then whatever percentage of each element was in there is going to be that many grams of that element that's in there. So we've got 100 grams of ibuprofen, which means that we've got 95.69 grams of carbon and 8.80 grams of hydrogen and 15.51 grams of oxygen. Okay. Now, in order to find the empirical formula, we got to get out of grams and get into moles, which means we have to use the molar mass for each one of these elements, just like we did in the previous problem. So the rest of this problem is going to be pretty much identical to what we did before. The only big variation was what we did here at the beginning. And our clue for which way to go was this percentage right here. Right? So knowing that we can take this percentage, when we're given this sort of information where it's like, oh, carbon is this percentage and hydrogen is this percentage and whatever else is that percentage, we can basically take these percentages and turn them into grams and apply them to 100 grams of whatever it is we're talking about. Okay? All right, so let's find the moles of each one of these. So we're going to take our 75.69 grams of carbon and we're going to multiply it by its molar mass inverted. Because remember, we're getting rid of grams and we're moving into moles. So we're going to multiply that by 1 mole of carbon over 12.01 grams of carbon, get rid of our repeating terms, and it's going to give us 6.3 moles of carbon. We're going to do the same thing for hydrogen and its molar mass. Get rid of repeating terms, do the math, and we get 8.73 moles of hydrogen. Don't worry about these numbers because we're going to manipulate them. We got some other steps. We're going to clean them up a little bit. And then we're going to do the last thing for hydrogen, its molar mass, and 0.97 moles of oxygen. All right, now we've found the moles of each one of these, but we have to establish a relationship, right? So we're going to take the lowest number of moles over here, and then we're going to divide all three numbers by that value. So the lowest number now is this 0.97 thanks to our oxygen. So for carbon, we're going to take 6.3. We're going to divide it by 0.97. That's going to give us 6.5. For hydrogen, we're going to divide 8.73 by 0.97 rather, gives us 9. And we're going to divide oxygen's value by itself, which is going to give us 1. Now, we said previously that these values would be the subscript in the empirical formula, but we got a problem with the 6.5. So the way we're going to resolve that, we're going to multiply it by 2, and that will give us a whole number, right? So 6.5, we can't put that in a subscript for an empirical formula, but if we multiply it by 2, that will give us 13, and that's a whole number, which means we have to multiply the other two values by 2 as well. So we're going to multiply 9 by 2, which gives us 18, and then 1 by 2, which gives us 2. And now we've got the subscripts that are going to go in our formula. So for carbon, we've got 13 of those. For hydrogen, we've got 18 of them. And for oxygen, we've got 2. And that is our empirical formula for ibuprofen. Now, your book is going to give you a chart that tells you what you have to multiply by in order, if you have a decimal in in this division process right here. This was pretty straightforward because in order to get rid of this 0.5, you just multiply by 2. But what if you had something like 0.33? Well, then you'd have to multiply by 0.66. And what if you had something like 0.66? Well, then you have to multiply by 0.33. So there's a chart that kind of makes this thinking part of it easy for you. And you can look at that chart. That's allowed. You just have to know how to use it. Okay? But that's basically what you want to do in this step. Get rid of that decimal. Whatever it takes, you have to multiply the rest of the values by that amount as well. In problem 4.16, we're continuing to build on our understanding of empirical formulas and what they mean. And what we're being asked in this problem is that we're given the empirical formula and the molar mass of it, and we want to know how to find its molecular formula. All right, so our givens are the molar mass, which is 78.11 grams per mole of this CH, and we know what the empirical formula is, which is CH, and we're being asked to find what the molecular formula is. And I'm giving you a pseudo molecular formula right here, which says that we have to basically figure out what these N's are. What is this value for N? And that's really the question, right? How do we calculate N? What is it equal to? Well, it's going to be equal to the molar mass of our molecule over the empirical formula molar mass. And we can calculate that pretty easily. So we're given the molar mass, we're given that right here. And so we just have to calculate the empirical formula molar mass, which is pretty simple. So we've got CH, which means we have to find the molar mass of carbon, which is 12.01 grams per mole, and the molar mass of hydrogen, which is 0.008 grams per mole, and then add those together. And that gives us 13.018 grams per mole of our CH. And so this is the value that we're going to plug in down here. So for our N, we're going to take our 7811 and put it over our 13.018, and we're going to do the division, do the math, and our N comes out to 6. And what are we going to do with this N? We're going to plug it into the formula right there. So for our molecular formula, where we've got C, N, and H, N being equal to 6, that means our molecular formula is C6H6. In problem 4.17, we have a combustion reaction, and our products are 1.6 grams of carbon dioxide and 0.819 grams of water. And they're telling us that the compound that underwent the combustion was a hydrocarbon. It only contained carbon and hydrogen. But if we look at our products, we can see that they both contain oxygen, which means that they combined with oxygen from the atmosphere. And that's how we ended up getting carbon to combine with oxygen and hydrogen to combine with oxygen as well. Now, given the amounts of the products, we should be able to come up with the empirical formula, even though we now have oxygen added to the mix. So let's take a look at what we're given. We're given that we have 1.60 grams of carbon dioxide and 0.819 grams of water, H2O, and we need to find the formula for our hydrocarbon, which is going to be C and with some sort of a subscript, and H with some sort of a subscript. So we got to basically figure out what those moles are in order to get there. And we know that we're going to have a relationship between the grams here and whatever these moles end up being. But we've got this complicating factor of the oxygen. So how are we going to deal with that? Well, the first thing we need to do is we need to figure out how to find the moles of carbon and hydrogen. And we're going to start with what we're given, which is to take a look at carbon dioxide and going to use molar mass. We're going to find the molar mass of carbon dioxide. So we're going to take the molar mass of carbon. We've only got one of those in the formula. And to that, we're going to add the molar mass of oxygen. We've got 2 of those in our formula. Going to do a little bit of that math, which brings us to 12.01 grams per mole of carbon plus 32 grams per mole of oxygen, and add that together, and our molar mass of carbon dioxide is 44.01 grams per mole. All right, now we know that we have 1.6 grams of carbon dioxide, and we can multiply it by this molar mass of carbon dioxide in order to get to the moles of this 1.6 grams of carbon dioxide. So that's what we're going to do. So we're going to take the inversion of the molar mass, put the grams on the bottom, the moles on top, because moles are the units that we seek, get rid of our repeating terms, and do the math, and we end up with 0.03636 moles of carbon dioxide. All right, so what we know about carbon dioxide is that we have 1 mole of carbon in 1 mole of carbon dioxide, which means that we are going to have the same number of carbons, moles of carbon, as we have moles of carbon dioxide, which means that we're going to have 0.03636 moles of carbon in 0.03636 moles of carbon dioxide. So that's how we're going to calculate the moles of carbon. Now we're going to do the same thing for water. So we're going to figure out the molar mass of water. So we're going to take our hydrogen. We've got 2 of those. We're going to take the molar mass of oxygen. We've only got 1 of those. We're going to do this math that's involved. So we're going to multiply out the hydrogens and bring down the oxygen and add that all together. And the molar mass of water is going to be 18.02 grams per mole of water. And we're going to take the amount of water that we got from our combustion reaction, which is 0.819 grams of water, and we're going to multiply it by our conversion factor, which is our molar mass flipped upside down, because we want to convert grams of water into moles of water. So we're going to get rid of our repeating units, and we're going to do the math, and that's going to bring us to 0.04546 moles of H2O. All right, now what we know about water is that we have 2 moles of hydrogen in 1 mole of water, which means that we're going to have to take this molar mass that we just calculated, and we're going to have to multiply it by 2. And that means that we are going to have 0.09092 moles of hydrogen in our in our product. There we go. Just lost the words. Okay. Now we figured out the moles of carbon and the moles of hydrogen. And the next thing that we have to do is we have to figure out what this N is going to be for each one of our elements. And the way that we do that is we look at the 2 elements, the values of the mole, and we're going to take the one that is the lesser, and we're going to divide them both by that mole value. And if we look at what we have with carbon and what we have with hydrogen, we can see that carbon comes in at the lower value. So for carbon, we're going to divide 0.03636 by 0.03636, which will give us 1. And for hydrogen, we're going to take 0.09092 and divide it by 0.03636, and that's going to give us 2.5. Now, we can't use a fractioned number or a number with a decimal as our subscript in our formula. So we've already dealt with this 0.5 before in a couple of other problems. And we know that we can multiply this by 2. And if we multiply this value by 2, we also have to multiply this value by 2. So we're going to multiply the moles of carbon by 2 and the moles of hydrogen by 2 and work those out. And so we're going to end up in our formula with 2 moles of carbon and 5 moles of hydrogen, giving us a molecular formula of C2H5. So for problem 4.18, we're going to be putting all of this together plus one more little twist. So we're still going to have to find the empirical formula given some products. So our problem says that we're going to combust this compound. We don't know what it is. We know that we started off with 0.8009 grams of it. And that it's only made up of carbon, hydrogen, and oxygen, and that during a combustion reaction it produced 1.6004 grams of carbon dioxide and 0.6551 grams of water. And so from this information, they want us to calculate the empirical formula. Now, we know that when a substance undergoes a combustion reaction, it can pull some oxygen in from the atmosphere. But in this particular problem, they're telling us that our compound contained oxygen already. And so the oxygen is going to be of the compound is what's going to be utilized in the combustion reaction. Because remember, we still have to abide by the law of conservation of mass. So however many elements entered into this reaction, we have to account for them at the end of it. And they're telling us that at the beginning, contained in that 0.8009 grams of whatever underwent this combustion, that is going to contain all the carbon, all the hydrogen, and all the oxygen that this combustion reaction utilized. So we are bound by that number, and we're going to have to use that number in order to come up with the value for our empirical formula. All right, so I'll course guide you as we go through this. I always like to start by writing down the givens. So we're given that we have the mass, an initial mass of a compound, 0.8009 grams of it, and that we ended up with 1.6004 grams of carbon dioxide and 0.6551 grams of water. And we're being asked to find what is the empirical formula for this substance that is made up of carbon, hydrogen, and oxygen. Now, with all these problems, the things that we've started with is we had to convert the grams into moles. Now, we're going to convert carbon dioxide and water into, we're going to find the moles of carbon and the moles of hydrogen, just like we did on the previous problem. And we're going to come at the oxygen in a different way. Now, why aren't we also solving for the moles of oxygen? Well, it's a little bit hard because we've got some of those moles here, and we have some of them here too. So we're going to have to kind of back in to finding our moles of oxygen. But if we can find our moles of carbon and hydrogen, then we can come back and utilize this starting value and figure all that out. Okay, and I'll show you how we're going to do that. So what we're going to do initially is going to be identical to what we did in the previous problem. So we're going to have to find the molar mass of carbon dioxide, which we've done before. We know it's 44.01 grams per mole, and we're going to do the same thing for water, which we know is 18.02 grams per mole. And we're going to take what we produced in grams, and we're going to convert it into moles using these molar masses. So for our carbon dioxide, we had 1.6004 grams of carbon dioxide, and we're going to multiply it by the molar mass of our carbon dioxide. And remember, the units we seek are going on top. The units we're eliminating are going to go on the bottom in our conversion factor, and that's what molar mass is for us, a conversion factor. So we can get rid of the repeating terms, do the math, and we're going to find out that we have 0.03636 moles of carbon dioxide. We're going to do the same thing for water. So we're going to take the amount of water that we had as our product, and we're going to multiply it by our conversion factor, which is the molar mass of water, making sure to put the units we seek on top, which in this case are moles. Get rid of repeating terms and do the math, and we end up with 0.03636 moles of water. Now, we don't really want to know the moles of carbon dioxide or the moles of water. What we're interested in are the moles of carbon and the moles of hydrogen. That's why I write this right here. So as I'm kind of going through these steps, I don't easily lose my way. All right, so what we know, just looking at carbon dioxide, is that there is 1 mole of carbon in 1 mole of carbon dioxide. Therefore, we can say that we have 0.03636 moles of carbon. But for water, we know that we have 2 moles of hydrogen in 1 mole of water. So we're going to have to take that 0.03636 moles of hydrogen, multiply it by 2, and that will give us the moles of hydrogen that we need to work with. And that value is going to be 0.07272 moles of hydrogen. All right, so that looks pretty good. So what are we going to do next? Well, we're going to back out of moles, because what we found with these values right here is we found the moles of our products. Okay, that's what we found, were the moles of our products. But we want to convert that back into grams of carbon, grams of hydrogen, so we can find the grams of oxygen. So I'll say that one more time. So we were able to take the grams of carbon dioxide and find the moles of carbon. We were able to take water and find the moles of hydrogen, and we're going to back into finding the grams of carbon and the grams of hydrogen, so that we can then figure out what are the grams of these this oxygen right here in these two products. All right, so how do we find the grams of carbon? Well, we're going to take the moles of carbon that we just calculated were in our product, which is 0.03636 moles of carbon, and we're going to multiply that by the molar mass of carbon, making sure to put the moles on the bottom because those are the units we're trying to get rid of, and move into grams of moles, so that's going to be on top. Get rid of our repeating units because that lets us know we've set up everything just right, and we're going to do the math, and we end up with 0.4367 grams of carbon. We're going to do the same thing for hydrogen. So we're going to take the amount of the moles of hydrogen that we just calculated, 0.07272 moles of hydrogen, and we're going to multiply it by the molar mass of hydrogen, making sure to put the grams of hydrogen on the top in our conversion factor and the moles on the bottom. Always like to get rid of repeating terms just to make sure I set everything up okay. And then do the math, and we end up with 0.0733 grams of hydrogen. All right, so at this point I've run out of room on my slide, and I'm going to have to move to a new one. So we're going to carry some of these numbers forward and keep on with our calculation. Now we have found the grams of carbon and the grams of hydrogen that were produced, and we can back these out of what we started with, the mass of our compound that we started with, because remember, conservation of mass requires that whatever we started off with as far as grams, we're going to have to end up with in grams. So we can take our compound and back out the mass of carbon and the mass of hydrogen and figure out how much oxygen we have. So we're going to find the mass of oxygen in the compound, and we're going to take the mass of our compound, which I'm just arbitrarily calling Z, I don't know what it is yet, and we're going to subtract the mass of the carbon, and we're going to subtract the mass of the hydrogen, and that's going to give us 0.2909 grams of oxygen. All right. Now, we've done a lot of work at this point, but we're still not done, because our question is asking us to find the empirical formula, and we know that grams don't help us find that. So we're going to have to convert all these grams into moles again. All right, and fortunately for these two values, we've already done that, but we haven't done it for oxygen. So let's go ahead and do that for oxygen. So we're going to take the grams of oxygen that we have, that we started off with, going to end up with as well, and we're going to multiply it by the molar mass of oxygen. Going to make sure we put the grams on the bottom because we're looking for moles of oxygen. Get rid of our repeating terms. It lets us know we set up everything just right. Do the math, and we end up with 0.01818 moles of oxygen. Now, once again, I'm at the end of my screen. I'm going to have to carry some values forward. Now, they're not on this slide, but they were on the previous slide. We had already calculated the moles of carbon and the moles of hydrogen. We had 0.03636 moles of carbon. We had 0.07272 moles of hydrogen, and we just calculated that we've got 0.01818 moles of oxygen. So we're going to carry these three values forward and continue on to figure out what the empirical formula for this compound is. So these are our three values, and the top one is for carbon, the middle one is for hydrogen, and this one is for oxygen. Now, we're at the point in our calculation where we have found essentially the moles that are going to go into our molecular formula, but we can't use these fractions. So the way that we eliminate the fractions is we look at which one of these numbers is the smallest one, and we're going to divide them all by that number. And we can see that it's the value for oxygen right here. So we're going to divide our moles of carbon by the moles of oxygen, and we're going to do the same thing for hydrogen and as well as oxygen. And when we do the math, we see that when we divide 0.03636 by 0.01818 for carbon, that's going to give us a value of 2. When we take 0.07272 and divide it by 0.01818, that's going to give us a value of 4. And of course, dividing 0.01818 by itself is going to give us a value of 1. And at this point, we have found what's going to go in the subscript of our molecular formula. So the molecular formula for this compound is going to read that we have 2 carbons, 4 hydrogens, and 1 oxygen. And with that, we're done. And with that, we're done with Unit 4 homework. And I hope the thing that you took away from this is the importance of staying really organized in doing your problems and making sure that you write down why you're doing each one of these steps. Because as you can see, it's really easy to get lost, particularly in a problem like 4.18. So be sure to review these because you'll probably see problems like this again. And I'll see you in the next one.